So last session, we started with mixup, just to recap a little bit. And the idea of mixup is not that complicated. You take the image of when you're actually implementing this, you take the image of a cat, you take the image of a dog, and then you create the convex combination of the two. So that's going to be the image of half a cat and half a dog. And that's how you're augmenting your input data. But then if your input data is no longer a cat, it's no longer a dog, the label, the corresponding label, should also match that. So it shouldn't be a cat, it shouldn't be a dog, but it should be something in between. So that's the intuition. And this lambda is going to tell you how close you are to a cat and how close you are to a dog. Lambda, you can sample it uniformly, the uniform distribution, or you can sample it according to a beta distribution. Why would you do that? Because they're going to have another hyperparameter that you can control, and then it's going to control how close you want to be to your actual empirical distribution. Basically, how close do you want to be to the dog and to the cat, and sample less frequently in between or more frequently. If alpha is exactly 0, you're back to a regime where you're just sampling from your data. No data augmentation is going on. But it turns out that for some of the problems and some of the networks, your alpha should be 0.2, and these you obtain it, it's a hyperparameter. The way that you set it is using your validation data. And for some other architectures, it's 0.4. And as you can see, all of them are shapes like this. So you're sampling more frequently next to your data and less frequently in between. And then you do your training, and in all of those cases, you're reducing your error, the top 1 error and top 5 error. Before I continue, are there any questions about mixup? So there is a question in the chat. Are there instances where setting a higher lambda value will cause the network to have more confusion about a cat and a dog? Of course, and that's the role of this alpha. By controlling alpha, you're basically controlling your lambda. And as you can see, for some of the networks, a different alpha is doing better. But if you mean alpha being or lambda being example dependent, no, for mixup, it's not. Then that's going to be too much as a degree of freedom. If you're saying lambda to be a function, so no, it's not going to be. That could be some ideas for future research, but then the way that you want to set lambda is you're going to have to work with your validation data. You're not going to be able to work with your training data. Okay. The question is, will similar techniques be important in transfer learning? So we haven't yet covered transfer learning. We are going to cover that later on in the course. So I can only give you a vague answer. Maybe yes, maybe no. But these are helpful as a data augmentation technique. So whenever you want to augment your data and you want to be agnostic to the type of the data, then mixup is a good choice. You can try it and see if it helps your problem. Okay. The idea is that you don't have to always work with empirical risk. Any other questions? Okay. There is another question in the chat. In the table, is ERM using repeated data to match the size of the individual epoch for mixup? Not really. So as you can see, the size of your data now is going to change. And the way that you're actually going to implement this, we know that you're not going to process all of your data at once. It's not going to happen. You're always going to take a look at mini batches of your data. So in reality, the way that you're going to implement this on a computer is you have a batch of 32 images and their corresponding labels. These are your real data. And then you take pairs of data from your mini batch, you sample a lambda accordingly, and then you create the image in between. And then you push that through your architecture, get your mini batch loss. So you're still going to sample from your data, a mini batch, create a convex combination, push that through your network. Does that answer your question? But your epoch is still epoch. It's one round of going through your entire data. And you're going through your entire data in mini batches, maybe in 32 examples at a time. Okay, any other questions? Perfect. I'm including GANs here, a little bit of GANs, to tell you, to convey this idea that mix-up is a general data augmentation technique. And when you have some sort of classification, it's going to help you. Or it's one of the methods that can potentially help you. So you have to investigate it in your problem. So far, what we have been doing was discriminative. It means that somebody gives you the image of a dog, the image of a cat, and then you're going to discriminate between the two and say, that's a dog, that's a cat. So that's a classification task. For GANs, generative adversarial neural networks, you are going the reverse route. Somebody give you, especially in the conditional case, somebody can give you a label. For instance, the label could be a cat, and then your task is to generate images of cats or images of dogs. So that's the idea. So it's the inverse of discriminative, generative inverse of discriminative. And you're basically learning the underlying distribution of your data, or at least learning to sample from the underlying distribution. But what are you actually doing? So don't worry about this loss for a second. I'm going to focus on Z. We all know how to sample from normal distribution or a Gaussian distribution. So that's easy. We can sample from Z from a Gaussian distribution with mean 0 and some identity. And we can sample as many samples as we want. There is this observation that if you take those simple samples from a simple distribution like Gaussian, and you push them through a nonlinear function. In this case, our G is a neural network. It's a nonlinear function. It's a complex function. Then the distribution that you're going to get out of GZ could be potentially as complex as you want. It's not going to be Gaussian anymore. It's going to have multimodal distribution. It's going to end up being nasty. So you sample from a simple distribution, you push it through a complex function, and then the result is some complex distribution. So far, so good. And that we know how to do. We take Z, sample from normal, push it through a neural network, and that's going to give us G of Z. But then you're initializing your neural network on G with some random parameters. Now the idea is, how do you actually train G? You want the samples that are generated to look like cats. How do you actually train G? The idea is that we are really good at discriminative analysis. We are really good at classification. And so far, what we have been doing was just classification. So let's borrow ideas from classification. We are going to define a classifier, D, that's a neural network, like the type of neural networks that you have here and we were studying before. And its task is to classify between real images, images that exist in your data set, and the images that are being generated by your generator. So the role of D is to help you train G. So the role of your classifier is to help you train your generator. What is the corresponding label for real images? The corresponding label is 1. The corresponding labels for fake images is 0. Now you're going to write down your cross-entropy loss for D, and then you want to minimize with respect to the parameters of your discriminator. So you want your discriminator to be able to discriminate between real and fake images. Okay, so far so good. Now you're going to get a D. You're training it. You're going to get a D, and you know how to train it. Stochastic gradient descent. How do you train your generator? You want your generator to generate samples that are as close as possible to real images. It means that you want your generator to be able to confuse your discriminator. So it means that your generator is going the opposite route. It's trying to maximize this loss. So the discriminator is minimizing, generator is maximizing, trying to confuse a discriminator. And then you're going to do training. Maybe 5 steps of training D, 1 step of training G in your for loops, and then you're going to let it run. So that's the idea. Any questions about that? Is the big picture clear? I need to hear a couple of yeses before I move on. Okay, great. So that's the idea. Now we want to do data augmentation, and we want to use mixup. Previously, you had a label that was an integer. Here, your labels are 1 and 0s. So this guy is a 1, that guy is a 0. So the corresponding label is going to end up being lambda. Lambda times 1 plus 1 minus lambda times 0. That's going to give you lambda. And then you're going to create a convex combination between your real images and your generated images. So this is going to be a real image. That's going to be a generated image. And that's going to give you this loss. So it's a modification of GANs, where your label is just lambda, and then you're interpolating between a real image and a fake image. And then you're going to write down your loss function, which is basically your cross entropy loss, or negative of the log of your likelihood. Okay, why is it helpful? There is this problem with GANs that they are going to collapse into a single mode. So that's the idea of mode collapse. Let's take a look at it. Underlying distribution is this. You have a bunch of pins coming out of your space. That's your underlying distribution that you want to approximate with a GANs, with your generator. You start randomly, and then you do training, and then at some point it is collapsing. It's not able to converge, or it's picking only one of these modes, where it's going to pick one mode at a time. During training, sometimes it's going to focus on this mode of your distribution. Sometimes it's going to focus on the other mode. It's going to have trouble converging. Same thing here. It's collapsing to this mode, and it's not able to approximate this distribution. But then with a proper choice for your alpha, which is going to determine your beta distribution, which is going to determine how you're going to sample lambda, you're able to match the distribution and converge to multiple modes. So GANs are famous for not being able to train, but now you're able to train them, at least for this simple problem. We are gonna, in the second part of this course, we are gonna spend a lot more time on GANs and trying to generate as realistic images as possible. But for now, I wanted to convey the idea that mixup is a general idea for data augmentation. The question is, what are these points? This is actually your distribution. If you have a normal distribution, that's going to be only one of these, and then you're going to have zeros everywhere else. You're going to have a single mode. Here you have, I don't know how many modes, 1, 2, 3, 4, 5, 25 modes. Okay, so your distribution has 25 peaks. And then you're sampling from that underlying distribution. You're first approximating it and then sampling from it. That's the role of GANs. Does that answer your question? Okay, perfect. Any other questions?